Hi everyone, hope you all are doing well. I am Rana Prathap Singh Bondili, and today I am going to talk about my final project that I have done in this course. So this is my final semester at UNT, and I have done and I'm really excited for my graduation. And yeah, so let's dive deep into the final project that I have done in the past few weeks. So in the first part, I have written an essay after I've attended the seminar in the UNT Frisco campus. So I'm just gonna give you all a quick overview of what I have written in the essay. So I've talked about RNNs and LSTMs here. RNNs and LSTM play a very important role in advancing generative AI. So the topic of the essay is the seminar topic is journey of generative AI from Boltzmann distribution and Markov chain to large language model. The journey of generative AI began in 1868 with Ludwig Boltzmann developing the concept of statistical mechanics. Later in 1906, Markov chain brought the concept of Markov chain Monte Carlo simulation. The lens sizing model can be described as the earliest form of recurrent neural networks. Here, the concept of spins is closely related to the concept of neurons in modern neural networks. So here we go on and on. Then in later times, the McLaughlin-Pitts model was brought to our attention, which is one of the basic stepping stones to the artificial neurons that we know in the recent times. It laid the foundation for neural networks. They have introduced the concept of perceptrons, which is identical to the human brain, human biological neurons. Perceptron is the simplest neural network which can be trained to learn. This concept of perceptron is a landmark in the development of artificial intelligence and in the concept of neural networks. RNNs have been developed to handle sequential data processing tasks. The traditional feed-forward neural networks cannot contain temporal dependencies, but RNNs can. So this is a whole essay that I have written so far. Yeah. So now that concludes our essay. So now I'm going to talk about part two of my project report, which is a time series data set that I have collected. So the name of the data set of this time series data set is energy consumption time series data set. So this data set features consumption of electrical blower machine with time slots of 10 to 50 minutes. The time interval, it has the information of energy consumption of this electrical blower machines for every time interval of 10 to 50 minutes. To collect this consumption of electrical blower machine, the author has used an IoT device. We can measure the energy consumption by using the current and previous timestamps. If the energy consumption value is null or less than zero point 0.5, then the energy consumption is represented as a machine was off when the reading was collected during the specific time slot. So when coming to the data type, there are three data types here: the TXN date, TXN time, and consumption. So the TXN date denotes the date on which the observation was recorded. The TXN time denotes the time at which the observation was recorded, and the consumption denotes the amount of energy consumption in numeric terms, like in decimal points, like that. So the official website where I have gotten the data set is kaggle.com, and here is a link to the specific data set that I have collected. So the time series span for this data set is from 1st January 2022 to 9th February 2022 as recorded. So now we're going to talk about the part three of my project, which is the recurrent neural networks, simple RNN with sine wave data. So now first we are going to talk about the design of the simple RNN. So this is the design of the simple RNN. It has input layers, hidden layers in between, and the output layers. Here we can see the whole neural network architecture of the simple RNN network. It is completely connected network. As we can see, every layer is connected to every input layer is connected to every hidden layer, which is then parallelly connected to every output layer. Yeah. Here the hidden nodes are used to store the information and to allow the flow of information. These hidden nodes carry the information. The output nodes send the information to the input layer by using these hidden layers in between. The output layer sends the information in the form of gradients, and these hidden layers sends the gradients back to the input layer. But when these gradients travel back from these hidden layers, the gradients keep getting smaller and smaller to the point of vanishing, which is the vanishing gradient problem, which we are going to talk about, which we are going to talk more about that in the later sections. Yeah, but the vanishing gradient problem is addressed by the LSTM network, and it has overcome that issue. So now we're going to talk about the report of the sine wave data. Sorry. So here we have built, trained, and tested a simple recurrent neural network on sine wave data using the TensorFlow and Keras. First, we will import the necessary libraries and packages from Python. As we can see here, we have imported all the necessary packages like pandas, numpy, matplotlib, sequential dense times, and we have also gotten the time series generator, which is the basic for neural networks. Then we have also gotten the X array values, as we can see here. We have also generated a plot for the XY values by specifying its specific values. Then we will get a plot as following. This is the plot for the X and Y values. We have used a min-max downsampling to produce sine waves. This data has to be prepared after that, after we have done the min-max downsampling. Here we have used a min-max scalar as we have specified in this code. We have specified the length as 50, and we have also created batches. Batches is 1, and we have used the train series generator as we can see here. The length of the normalized train series generator is 666. Then we have trained the model as a sequential type. Here is the code for how we have built the model as a sequential type, as we can see. Here, this is the code for the building the model, and this is the code for the evaluating the model. We have used the compile time interpreter to evaluate the model. We have used the optimizer and loss functions as ANM and MSC, and we have gotten a summary of the model by using the summary method. Yeah, we have specified the length as 50. We have split the data into training and testing data. We have also built a simple recurrent neural network with 100 units and trained the model using the fit method and 5 epochs as parameters. We evaluated the model using the optimizer and loss as you just talked about now. We have also considered loss plot, which shows a decrease in loss values. When we have trained the model using the 5 epochs, we have gotten the loss values, and the loss values are as follows: 0.0029, 3.31, like that. And these loss values are in decreasing order, and that is a good thing to know. Yeah, that is a good thing for network. Then we have also gotten the total parameters, which are 10,301. We have also generated some test predictions for this model. We will compare the current and true predictions in this code. Yeah. Then we have trained the model using the fit method, as we can see in this code, using the train series generator and the 5 epochs. And then finally, in the sine wave data set, we have gotten the sine wave as is follow. Here we can see the comparison between the sine wave and the predictions. So that concludes the sine wave data set. Now we're going to talk about the RNN LSTM neural networks. So now first we are going to talk about the vanishing gradient problem, which is the first question in this topic. So we have come across a vanishing gradient problem in recurrent neural networks, which is a big issue and a very big drawback for recurrent neural networks. When we are using back propagation while training the neural networks, the gradients are calculated in each neural network by using the help of loss function. So what this means is, let me show you with the help of this diagram here. Of this, oh yeah. So in recurrent neural networks, the information is traveled from the output layer to the input layer by using these specific hidden layers. The hidden layers collect the information from the output layer and then sends it back to the input layer in the form of little gradients. These little gradients keep on traveling to the point, and every time they are passed from one hidden layer to the other hidden layer, they are shrunken down in size to the point where they are shrunken down to the point of vanishing, where they are completely vanished when they have reached the input layer. So they are completely vanished, and that is why it is called the vanishing gradient problem. So this completely slows down the training process as a whole, and that is a very big issue. And this issue is overcome by using the LSTM neural network, as we can see. Yeah. So yeah, I hope you all understood about the vanishing gradient problem as I just talked about. And then now we're going to talk about the exploding gradient problem. The exploding gradient problem is completely opposite of the vanishing gradient problem. Here, while training the deep neural network, instead of the gradients getting smaller in size, as we can see in this diagram, in the vanishing gradient network, the gradients keep getting smaller in size. But in the exploding gradient problem, when the gradients are traveling from the output to the input layer, the gradients keep getting larger in size to the point of where it becomes too much large for the model. So is this an issue, you ask? Yes, it is an issue. This can impact the training process again, and the updates to the network's parameters become too often. And the optimization process also becomes unstable because the gradients have gotten too large for the model. Here we can clearly see the difference between the vanishing and the gradient exploding problem in the figure here. So now we're going to discuss about the limitations of the simple recurrent neural network. Well, there are several limitations of the simple recurrent neural network, as we can see here. We have already talked about the vanishing gradient problem. Now we're going to talk about short-term memory. Short-term memory. The recurrent neural networks is limited in terms of storing information about earlier time steps over long sequences. There is no parallelism. Simple recurrent neural networks use sequential processing instead of parallelism, which slows down the training process. There is time lags. A simple recurrent neural networks suffer from learning relationships between events which are separated by many time steps that are known as time lags. So these are some of the limitations of the simple recurrent neural network. Now we're going to talk about this question here. So this question is as follows. Explain how the LSTM neural network can provide solutions to the gradient problems, which is the vanishing gradient, and then the exploding gradient problem, and also address the limitations of the simple recurrent neural network. So here, LSTM neural networks are designed specifically to address the issues of the RNN neural network and the gradient problems of the RNN network. Now we will discuss how the LSTM network has overcome those issues. The LSTM network has gating mechanisms. LSTM network has used the help of three gates, which are the input gate, forget gate, and the output gate, as we can see. It uses the help of the long-term memory. LSTM literally translates to long short-term memory. LSTMs do not have the vanishing gradient problem as they are designed to capture long-term dependencies in the sequential data. This happens by using the help of cell states in the sequence. Gradient problems. LSTMs use cell states and gates to ensure that the gradients flow more freely and are not susceptible to the vanishing gradient problem. LSTMs update the cell state and hidden states accordingly. Short-term memory. LSTMs also capture short-term dependencies by using the help of input gates that control the flow of information that flows through the cell state. So this is how LSTMs solve the gradient problems and address the limitations of the simple recurrent neural network. I hope you all got understood how the LSTMs overcome this issue. So this is the basic architecture of the long short-term memory neural networks. As we can see clearly here, these are the three gates of the LSTM network. This is the input gate, forget gate, and the output gate. It has one cell state and one tannage layer and three sigmoid activation functions, as we can see here. It has three sigmoid activation functions, while the RNA network has only one tannage layer. It has one tannage layer and also three sigmoid activation functions, three gates, and one cell state, which is very differentiated from that. So now we're heading into part 5, which is the RNN LSTM with time series data. So this is the basic architecture of the LSTM network. This figure more clearly explains about the LSTM architecture. See here, now I have talked about the sigmoid activation functions. This clearly shows the sigmoid activation functions. There are three sigmoid activation functions, one tannage layer, one cell state. So yeah, the gradient here, the information is passed from the output layer to the input layer using these gates. The gates control the flow of information from the output to the input. This LSTM architecture is clearly designed to overcome the issues of the RNA network. It has three sigmoid and one tannage layer. It also uses the help of gates, which are input, forget, and output. The flow of information is maintained by these gates, and it also uses cell states. So now we're going to go to a summary of these core parameters of this LSTM architecture. That I have used a data set, which is the Microsoft Stocks data set, MSFT from the Yahoo Finance website, and the percentage of data for testing is 10%. The number of neurons in each LSTM layer is 25 neurons in this LSTM layer. How many layers in LSTM layer? Two LSTM layers. There are 25 neurons in each LSTM layer. Any dropout layers? Yes, we have dropout layers. If it's a dropout layer, the percentage to drop is 20%, and the length of the time series input sequence is 288, and the batch size for training is 32, and the testing batch size is 1. The number of epochs of training are 100 parameters. So now we're going to talk about the report of the LSTM network. So the beginning is basic, like the RNA network. We are going to input the basic Python libraries, the pandas, NumPy, Matplotlib, sequential, LSTM, dropout, everything else. We are also going to use the min-max scaler as before. Now we're going to load the data set of Microsoft from the specific time span, which is from 1st November 2021 to 31st October 2023, which spans 2 years exactly. So yeah, here we're going to give the path of the Microsoft dataset in the code. All these Python libraries are from the TensorFlow modules, and then we have loaded as we can see. Then we have retrieved the statistics summary of a dataset as seen here. We have used the all.describe method for this. We have gotten the statistical summary of the dataset. These are the attributes of the Microsoft stocks: the open stock price, the highest point of the stock price, the lowest point of the stock price, the closing stock price, and the adjusted closing value, and the volume of the stock price. And these are the count, mean, standard mean, minimum 25%, 50, 75%, and the maximum value stock price. We have also generated a plot so we can see that shows the closing stock prices at different intervals. This is a very clear plot that shows the closing stock prices, and it's very important for those who want to invest in Microsoft. Now we're going to split the data set into the training and testing data sets. We're going to use this code to split the data set. The testing length is 50, as we can see, and we have split the indices also, as we can see here. There is a beginning index and the ending index. And then we are going to retrieve the first 5 rows from the after the splitting by using the head method. We have gotten the first five most recent training records, as we can see here, by using the head method, and we have split the index from beginning to ending. The first index will always be 0. Then we have built the model, a sequential model here. This is the code for building the model. We have built the sequential model by using 50 units and the activation ReLU activation function, and also specify the dropout layers. And then we are going to evaluate the model using the compile time evaluator. And we have also specified the optimizer and loss functions. The optimizer function is Adam, and the loss function is MSC. And then we have gained a summary of the model using the summary method. Then we have evaluated the model using the compile time evaluation and specified the loss in, as I just talked about now. Then we have observed that the total number of parameters is 50,851, and there are no non-trainable parameters as we can see. And then we have trained the model using the fit method here, and we have used 100 epoch as parameters and the train series generator for training the model. The train series generator is the building blocks of the neural networks. We have used a train series generator. We have also created time series generator to train the model. The time series generator and the transformer generator is these are the generators with the building blocks of the neural networks. We have also generated a loss plot and made some predictions on the testing data using the time series generator. We now for forecasting. Now we are going to forecast the LSTM network again. For forecasting concern, we are going to rebuild the whole model, re-evaluate, and also retrain. We're going to rebuild, recompile, and retrain. So for training the model, we're going to use the fit method again. We're using the forecast generator and the epoch values. The epoch values are the same, which are the 100. We are going to use 107 period values. We have also used batches this time for training using forecasting. So we have gotten a plot of for the closing intervals again, for the closing intervals of Microsoft stocks. So this is the plot for the forecasting So these are values for the forecasting. Then we have forecasters and plots for the close and forecast values, and in the end we have generated result and plot to compare between the close and forecast values, as we can see here. Sorry. This plot clearly shows the comparison between the close and forecast values. Now we're going to redesign the neural network. We have redesigned the LSTM neural network that I have talked about till now. It is very similar to the LSTM one. Only some of the parameters have been changed, and so because of that, we have not achieved that high bit of performance from the previous one. We have done this to increase the performance, but no significant change can be seen in the output. So this is the architecture of the redesigned LSTM network. The previous LSTM network has 25 neurons in each layer, but this LSTM redesign one has 50 neurons in each layer. So the summary of the updated core parameters are as follows. The percentage of data for testing is 10%. The number of layers is 2 as the same one as before. The number of neurons is changed, which is 50 neurons this time instead of 25 before. Yes, there are dropout layers again, and if the percentage to drop is 20%, the length of the time series input sequence is 288. The batch size for training is 40 and the testing batch size is 1. The number of epochs for training is 100. So now we're going to talk about the report. We have imported the Python libraries as always. The basic Python libraries, as we can see here, the pandas and numpy again. Then we have loaded the data set, which is the same data set as before and the same time span again, using the same load function. Now we Yes. Then we have retrieved the statistic summary of our data set, as we can see here. using the describe method, and the attributes are as same, but the values are almost values are as we can see here. There are a total of 60 elements in the input time series. We will be splitting the data into training and testing data sets. We will then retrieve the first 5 training records by using the head method and specify the data in the head method, the number of 5 in the head method. So here is the code to how to split the data into training and testing data set. Then we will normalize the data using the min-max scalar and create a time series generator for training and specifying the batch size as 32. Then we will build a sequential model. Here is the code for building the redesign LSTM model. Here is the code to how to evaluate the LSTM model using the compile time interpreter and using the optimizer and loss functions, as we can see, and getting the summary in the summary method. We have used a review attribution function for building the model. We have built a sequential model. Then we will train the model using the fit method, which is the we same as always. And we have used a train series generator and epoch parameter as 100. Now we have generated a loss plot, as we can see here. The loss values have completely decreased this time, which is a bit different from the loss plot of the LSTM. The redesign LSTM has a completely different loss plot, which was a high performance increase because the loss is very low. And yeah, this shows this is very important to show the strength of the redesign LSTM network. Sorry. Then we have retrained the model using the time series generator for forecasting regions. For forecasting, we are going to retrain the model, rebuild, retrain, and redo everything. We're going to also reevaluate the model again. So this is how we're going to build the model again using the fit generator, forecast generator, and the epoch parameters. Then we're going to do the forecasting using the LSTM network by using this following code, by setting the period values, by setting up the batches, and using the for loop to store the predictions. And in the end, we have gotten a resultant plot for close, as we can see in the here. So this is the closing stock price of the LSTM network. So yeah, this is a bit different from the LSTM previous one. This is the redesigned LSTM closing stock prices, as we can see here. So the redesign layer is clearly high in performance than the previous one. So now we're going to compare the network performance between the two. So here in this next section, we will compare the performance between the LSTM and the redesigned LSTM networks. Recurrent neural networks are RNNs are recurrent neural networks when we look at the performance category. LSTM clearly outperforms the RNNs. It can address the limitations of RNN and we outperform it. We can measure the performance by using the time steps. We will clearly forecast the values at next time step using the values of the current time step. So yeah, I'm just going to give a brief overview of the comparison between the two networks. All the forecasts will be stored in the testing data sets here. We will need batch size of 1 because we will be running 50 iterations of the LSTM model by using one neuron fit, and we'll be also making test predictions. Because of this, model fit will be a bit different. There is no significant change in the performance of these two models because the results are changed only slightly. We have changed the parameters of both the models though. Yeah, the parameters have changed. There is no significant change in the output because yeah, only some of the parameters have been changed. Every LSTM layer has 15 neurons instead of 25 neurons before. The redesign one has 50 neurons. Before one has 25 neurons, which is a clear change comparison. And the dropout percentage is increased from 10% to 20% by using the dropout layer. The training batches have also been seen as increased when we compared in both the networks. And the training epochs are also seen as increased between the new networks. So these are the clear comparisons that we can see between the two networks. So now we're going to talk about a brief overview of our project report that I have done so far. So first we're going to do about the introduction of the project. So the RNNs are the first starting neural networks. So they are the recurrent neural networks and they are the first starting building blocks of this whole thing. I'm just going to give you a brief overview again. Recurrent neural networks were invented because standard neural networks do not have the capability to send the information from the output layer to the input layer. But recurrent RNNs can do that with the help of the hidden layers in them. And but they suffer from the vanishing gradient problem and they have a lot of limitations. But these limitations are clearly explained by the LSTM and overcome by the LSTM networks. Long short term LSTM is known as long short term memory. is a term made up specifically for this issue for overcoming the issues of vanishing and exploding gradient problems. They have three gates, which are the input, forget, and output gate, and have three output or segment activation functions and one tan H function, and also cell state to overcome the specific issues of RNN. And yeah, the output of the LSTM networks come in binary format as 0 or 1. If 0 comes out, it's as rejected, and if it's 1, it's accepted. So what now I'm going to talk about what I have done so far in part 3, 5, and 6 of the final project. We have identified patterns and correlations in the data to generate prediction outputs for sequential data. In part 3, we have considered a simple sine wave by using the specific parameters, and then we have used new data set this time. RNNs are better understood when we look at the whole sequence. There is not too much modification in the data models. In the redesign one, not too much modification, but if significant performance change is achieved. LSTM offers solutions to the drawbacks of RNN, as we all know, and the redesign LSTM also created in part 5 and saved in part 6. Only the parameters have been changed. LSTM is very useful for long-term dependencies in various states. So what I have learned from these models, from the simple RNN and LSTM. Our LSTM are excellent in making predictions and storing data for a long period of time for long-term dependencies, but our RNNs have problems with short-term memory, but LSTMs are better at long-term memory and short-term memory. So we can say that LSTMs are clearly better at both. They have similar parameters to build train forecast model in both. Only some of the values have been changed or modified. We have built a sequential model in both the LSTM and RNN using the fit method. Yeah, we have also used a train series generator. Now I'm going to conclude the topic. So this course and project have taught us a lot about the neural networks. We first started off with the recurrent neural networks and delved deep into the advantages and disadvantages of the RNNs. We have then explored the concept of LSTM neural networks, which is designed to overcome the limitations of these drawbacks of RNN. LSTM clearly outperformed the RNN neural networks. RNNs only have hidden states to store the data, while LSTMs both have cell states, hidden states, and also use the help of gating mechanisms, the output, input, and forget gates, and also uses the help of cell states to control the order and flow of information. LSTMs are clearly the better neural networks than RNNs. They can store long-term dependencies and also address the vanishing gradient, exploding gradient problems. Even to this day, RNNs and LSTMs are used as a foundation in the learning of generative AI. And we can all hope that generative AI will be developed so much into the future, and the concepts of RNNs and LSTMs will always be as a foundation stones for neural network architectures for even in way into the future. And I really hope that generative AI will be developed so much into the future. And this concludes my presentation of this topic. And this concludes my presentation. Thank you everyone for listening to this. Thank you, Dr. Atwan, for giving me this opportunity to give a presentation on the project that I have done. And this is my final semester here at UNT, and it has been a wonderful 1.5 year of doing my masters. And and thank you, everyone. Thank you.